Hello, today I'm going to be going through the multiple choice from the 2018 paper 2, AS paper 2. So hopefully you've all had an attempt at this. Let's crack on. Right, these always cause people issues. It looks like a dilution question. A student has a 10 centimeter cube sample. So we've got a volume, we've got a concentration, V and a C, of methanoic acid solution, which is not important, but methanoic is one carbon, CH3C. Oh, no, it's not. C. Oh dear, let's have a go. That's methanoic acid. COOH. That's it. CH. Got a bit confused there. HCOOH. That's methanoic acid. I'll draw it out again here. It's not essential for the question. I just want to do it. That's methanoic acid. Right. The student is asked to dilute the methanoic acid, so they're going to add water to that methanoic acid to get the concentration down to. So what I like to do is concentration and volume before. The concentration was 1 times 10 to the minus 2 moles per decimeter cubed. The volume was 10 centimeters cubed. I'm happy with the units. And we want to get it to a new concentration of 2 times 10 to the minus 4, so from minus 2 to minus 4 moles per decimeter cubed. So what we really need to do is find out the new volume. There are very simple ways to do this, but I'm going to talk it through in the way that I like to do it because it's more adaptable. If I've got a C and a V, I like to turn this into moles. So concentration times volume, we're going to find out how many moles of methanoic acid there are, which is C times V divided by 1,000, which is 1 times 10 to the minus 2 times 10 divided by 1,000. 1 times 10 to the minus 2 times 10 is 1 times 10 to the minus 1 divided by 1,000. Bear with me because it's Sunday and I don't want to make mistakes. 0.01 times 10 equals divided by 1,000 equals 0.0001. 0.0001. So I've got this many moles. That many moles I'm now going to add a load of water to. So now I've got a concentration and a moles. So if moles equals C times V divided by 1,000, and I want to work out the new volume, I'm going to take the moles and I'm going to times by 1,000. Moles times 1,000 divided by C. So I'm rearranging that equation. So I'm just going to get my calculator here. Just got that previous answer on. It did have that previous answer on. Good start, isn't it? Slick. 0.0001 times 1,000 divided by 2 times 10 to the minus 4. 0.0001 times 1,000 divided by 0.002. 500. So the new volume equals 500 centimeters cubed. However, the previous volume was 10, so how much water did they have to add to get to 500? The answer is B. I hope the answer is B. I'm going to pause the video, just make sure I've got these answers right. So I'm going to get the mark scheme next to me. You probably won't notice the pause because it'll just carry on. Excellent. So I got that right. Now, I do want to just show you a nice little shortcut to this type of dilution question. If you've got a question like this where they say, how much water do you add to dilute something? What you're going to assume is the moles before equals the moles at the end. So what you're going to do is add water. You're not going to change the number of moles of, methanoic acid. So if moles before equals moles at the end, concentration times volume at the start equals concentration times volume at the end. So we know here that 1.1 times 10 to the minus 2 multiplied by 10 equals 2 times 10 to the minus 4 multiplied by the second volume. So you could just do this. 1 times 10 to the minus 2 times 10 divided by this constant divided by C divided by 2 times 10 to the minus 4, and you will get the answer of 500 centimeters cubed. But then the final bit of the trick here is you had 10 to start with, you've made it up to 500, so You just got to watch out for that. So it's 490 and not 500. Which molecule does not have a permanent dipole? So these are all got one carbon in. I mean, I've spotted the answer straight away because, and some of you might have, and they've all got a bromine in, which means they're all going to have a polar bond. So I'll just draw each of these out, CH3. So they're all carbons with 4 bonds on them, 1, 2, 3, 4. Hydrogen, 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 bromine. So this is going to be delta negative, delta positive. That's got a dipole because the dipole sort of looks like that. It's not a symmetrical molecule. This one's CH2Br2. If you had the Br here and the Br here and the H here and the H here, got delta negative, delta positive, 2 polar bonds. There's a dipole in that molecule. Long story short, if you've got bromine, 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 and bromine, each of these bonds individually is polar, but the molecule itself is non-polar because it's symmetrical. The answer is D. In an exam, I hope you'd spot that and just move on, do it dead quick. Right, looks like I've printed this back to back. Which is a major product of the reaction between 2-methyl-butadiene and iodine monochloride. I remember doing this one in class with you. 2-methyl-butadiene, butadiene, 2-methyl. I'm just looking at the way they've drawn it here. So they've counted from this side. So 2-methyl-butadiene. I'm just going to put that up there. Okay, there's 2-methyl-butadiene and iodine monochloride. Iodine monochloride, we don't do any reactions with iodine monochloride, but the idea is that you should know that iodine monochloride, the chlorine is more electronegative than the iodine, so you'll have a polar molecule that looks like that. That means that when this polar molecule is attracted to this double bond, it's going to act a little bit like HBr acts, delta positive and delta negative. And you know a mechanism for this, it's electrophilic addition. So I'm going to draw this out. I mean, again, it's one of those, I've spotted the answer straight away, but it's whether you lot do. You're going to get I bonding to Cl, Cl minus and I plus. The first step, the I delta plus will add on. That will create a carbocation, and the Cl minus will then attack where that carbocation is, and you will form the product that's formed through the most stable carbocation. So what you're going to get is you're going to get I and Cl bonded over this double bond. The double bond will disappear. So you're going to have an I and a Cl, an I there and a Cl there, or an I there and a Cl there. So first thing we can do is just dismiss this one, because it's got the I and the Cl adding in the wrong place. And we can therefore dismiss this one, which has got the I and the Cl bonding in the wrong place. So now you're left with this one and this one. Now we know from the mechanism that the chlorine or the chloride actually adds second. So what we can do is you can just sort of take this back. That means that this must have been the carbocation with the chloride attacking there. And in this case, this must have been the carbocation with the chloride attacking there. And now you've just got to ask yourself, in C or D, which is the most stable to carbocation? Well, this carbocation is a tertiary carbocation, and this carbocation is a secondary carbocation, so the answer is C. And if you asked in the exam, you would say because it forms via a tertiary rather than a secondary carbocation, and tertiary carbocations are more stable than secondary carbocations. So that was the answer to that one. Which statement is not correct about the industrial preparation of ethanol by the hydration of ethene? Right, so let's have a little look here what we've got. So we've got an equilibrium. It might be asking us about equilibria. It's exothermic, which means it releases heat. You've got 2 gaseous molecules on this side, 1 gaseous molecule on this side. And the fact of the matter is you're meant to know about this process. So you're meant to know the reaction conditions. And some of you, a lot of you actually, just think, if you're sitting there going, I don't know the reaction conditions, you're in the minority. If you're somebody who's going to ask me next year to predict you an A or a B or whatever it might be, you do need to know things like this. So the industrial preparation of ethanol by the hydration of ethene at 300 degrees is catalyzed by an acid. So which statement is not correct? The higher the pressure, the higher the equilibrium yield. So let's have a look at that. If you increase the pressure, the equilibrium will shift to the side with the fewest gas moles to release the pressure. So if we increase the pressure, the equilibrium will shift in this direction because there's 1 gas mole over here and 2 gas moles over here. So this is true. And remember, we're after which one is not correct. The higher the temperature, the higher the equilibrium yield of ethanol. Well, the way that I remember this, you just got to remember one fact. With equilibria, if you increase the temperature, it will shift in the endothermic direction. In N. If you increase the temperature, it will shift in the endothermic direction. So if we increase the temperature of this, well, this is telling us that it's exothermic forward, it will shift in this direction, which will not make more ethanol. So this is the one that's incorrect. All right? Remember this, in N. A low equilibrium yield of ethanol is acceptable because all unreacted ethene is recycled, which is true. All right. So far, so good. For me, anyway. I'm having a nice time. Which compound has the highest boiling point? And what we notice here is you've got 4 organic compounds. So this is going to be a question. See, these are all molecules. So if we're being asked about boiling points of 4 different molecules, we're being asked about intermolecular forces or weak intermolecular forces, of which there are 3 types. There are van der Waals, there are permanent dipole, and there are the other one, H-bonds. All right, so this is going to be a question about look at these molecules and decide what sort of intermolecular forces they've got, and there will be one standout one that's got the highest intermolecular forces. Straight away, I'm looking at B. It's got an ol in it, which means it's got an OH in it, which means it can do hydrogen bonds. This one can hydrogen bond. The answer is going to be B, because that's the strongest weak intermolecular force. Let's just look at the other ones, though. Butanal, 1, 2, 3, 4, This cannot hydrogen bond because it has not got a hydrogen bonded to an N, an O, or an F. It's got an oxygen, but it hasn't got a hydrogen joined to this oxygen. So this can do permanent dipole. This can do hydrogen bonding. Butene, van der Waals, 1-fluorobutane. 1-fluorobutane. Yes, it's got a dipole, but it's got no hydrogen bonding. Literally, that should take you seconds in the exam. If you know this is about intermolecular forces, you go, right, okay, which one's got hydrogen bonds? U. Which statement is correct about the fractional distillation of crude oil? Well, fractional distillation of crude oil is... I'm not looking at the question yet, I'm just doing a little bit of revision as I go. Heat it evaporates, rises up the column, cools as it rises, condenses, and you collect it. A zeolite catalyst is used. No, you don't need a catalyst in fractional distillation, you just heat it up. Each fraction contains a mixture of hydrocarbons. Yes, it does. B. God, that's easy. Gaseous fractions are formed by breaking covalent bonds. Nonsense. Gaseous fractions, you're breaking weak intermolecular forces. The fractionating column is hottest at the top. No, it isn't. It's hottest at the bottom. If you're getting that wrong, you're not doing very well, are you? Look back over fractional distillation. It's, again, I always default to this saying it's not hard, but that genuinely isn't. You know, you all chose A-level chemistry because you did all right at GCSE. Surely you understand fractional distillation. How many structural isomers are there with the formula C4H8Br2? Now, I'm nervous about this because, as I've said in a previous video, I tend to get these wrong in class. So let's see if I can be systematic. There's 4 carbons. So unbranched, so they're not going to let me do any... They don't want me to do anything like this. Okay? No branches. So it's straight chain. So I may as well draw some 4 in a rows. Some 4 in a rows. Some straight chains is what I should have said. Not some 4 in a rows. I'll just draw some and see how many different ones I can manage. C4H8Br2. Alright, let's assume that there are all the hydrogens are there. I've got 2 bromines to put in a position. So let's start off, let's be systematic. I could put a bromine there and a bromine there. The rest are hydrogens. I'm going to keep this bromine here. I could put a bromine there and a bromine there. I could put a bromine there and a bromine there. These are all different so far. I could put a bromine here and a bromine there. Bear with me, I'm not done. I know I'm not done. Right, so that's the variance of like moving the a bromine along one. I could then have a bromine on this one and a bromine on this one. There must be another one. Ah, yes, and a bromine there and a bromine there. Come on, Norton. I think I'm gonna go with 1, 2, 3, 4, 5, 6. I'm gonna go with 6, but I'm fully aware I might have got that wrong. Am I missing something? It's normally one of you lot think, no, sir, you've missed this one. I don't think I've missed any there. Let's check the answers. I'm just going to log on again. Questions are 15C. Yay! Cool. Let's just check the others while I'm there. 14B. 13B. 16, Maxwell Boltzmann. Right, these are easy. These are easy, right? Energy E, number of molecules with energy E. The Maxwell Boltzmann distribution of molecular energies in a sample of gas at a fixed temperature is shown. What letter represents the mean energy of the molecules? Right, the mean energy is D. Alright? A and B, neither of those represent energy. A and B represent number of particles with certain energy. C, does anyone know what that is? I know you can't hear me, but I can't hear you, sorry, but it means that C is the most probable energy. That's right, well done at the back. Okay, ethanol can be made from glucose by fermentation. In an experiment, 268 grams of ethanol were made from 1.44 kilograms. You're not catching me out, mate. 144 kilograms, that's 1,440 grams, which has got an MR of 180. What's the percentage yield? Okay, percentage yield questions, never just divide two numbers by each other. It's not going to work. A percentage yield is, in very simple terms, it's what you got, what you got divided by what you should have got times 100. All right, I know it's not very scientific, but it's what you got divided by what you shouldn't have got. In other words, it's the yield divided by what you should have made, the maximum yield you could have made. So to do this, there are two parts. Let's work out what you should have got first, and that's doing a reacting masses calculation. So 1,440 grams of this should have made, so what we're going to do is going to turn this into moles divided by 180. That'll tell you how many moles of glucose you've got. Oh, stupid calculator. Daughter's phone again. Let's remember her password. Okay, so 1,440, clear that. 1,440 divided by 180 equals 8. So we're starting off with 8 moles of glucose. 8 moles of glucose, this is reacting a 1:2 ratio. You should make 16 moles of ethanol. So I'm going to times my 8 by 2. Get 16. You should make 16 moles of ethanol. Ethanol has an MR of 46. So if I times 16 by 46 times 46, you should have made 736 grams. All right. So that's what you should have got, 736, but you only made 268. 268 divided by 736 times 100. 268 divided by 736 times 100, equals times 100, 36.4%, B, 17B. They're really straightforward, as long as you realise that yield questions, they require you to do two things. Firstly, work out what you should make, and then you say, well, I did make this. So you should have made 736, but you only made 268. Find as many of those as you can, just do them again and again. You realise that they're not hard. Which species could act as a nucleophile? So a nucleophile is a lone pair donor, so we're looking for anything with a lone pair. A nucleophile, lone pair donor. Whoops, what does LCP mean? Lone pair donor. LCP? Where are we getting that from? Alright, So we know that like OH minus can act as a lone pair, or nucleophile, or NH3 or Br minus. All right. Right, not you. Boron is in group 3. It's got 3 outer shell electrons and then it's got 3 hydrogens on. It ain't got any lone pairs. NH4 plus is not going to be a nucleophile. NH3 looks like this. NH4 plus has got the lone pair is being used for a coordinate bond, so it's not you. pH3, it's that one. Phosphorus is in group 5. 1, 2, 3, 4, 5. 3 hydrogens. 1, 2, 3. It's you. You've got a lone pair. Phosphorus and nitrogen are in the same group. pH3 is very similar to NH3. It's got a lone pair. SiH4, that's a group 4. That's like CH4, because silicon's in the same group as carbon. Has CH4 got a lone pair? No. pH3, has that got a lone pair? Well, you look down the group, has NH3 got a lone pair? Yeah. There's another way of doing it. Which statement is correct about polychloroethene? So you need to know about polychloroethene. Specifically, there's a little paragraph on it. There's a double page like that in there about polymers. And it's down here a little bit about PVC. It's called polychloroethane or PVC. Can't remember what page that is. Is it like the diagram? It's good, that, isn't it? But it's down there on a double page in your textbook. Right. PVC then. Question 19. Let's have a little look through these little bits. I'm going to see if there's any obvious ones first. Don't think it's got that. Actually, I'm just going to go through. It doesn't decolorize. I'll come back to that one. But first I'm going to see if there's an obvious answer. I don't think it's that. No, it doesn't decolorize bromine water because once it's a polymer, I know it says ethene there, but a polymer opens up its double bonds, doesn't have double bonds. Its brittleness is reduced by plasticizers. That's true. That's true. Don't need to look at any of those. Its polymer chain consists of alternate single and double bonds. No, it doesn't. It's polymer chain. So chloroethene looks like this. So polychloroethene. Wait a minute. Looks like this. There's no double bonds in that. It was C. You know what I mean? You could look at each question one at a time and go, is it you? Is it you? Which sometimes works. But really, there's sometimes just a really obvious answer. Brittleness is reduced by plasticizers. What's the enthalpy of formation of buta-1,3-diene? Okay, let's draw an equation. Write an equation first. The enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states. I'm not reading that. You know I'm not reading that. You just know these things. Right, elements in their standard states. 4 carbons. Pen's dying a little bit here. 4 carbons, solids. 3 H2s, gas. And we're trying to work out this, X, the enthalpy of formation. And they're giving us enthalpy of combustion. So I'm going to burn this enthalpy of combustion. So if you burn something, it turns into something else, doesn't it? And that is minus 2,546. I've used this value. You'll make carbon dioxide and water, by the way. You'll make 4 CO2s and 3 H2Os. I'm now given the energy when you burn 4 carbons. So that's going to be 4 times minus 394. 4 times minus 394. Pens come back to life. Excellent. And I'm going to burn... This is the energy I've used up. This is the energy when you burn 1 H2. And we've got 3 of them. So it's going to be 3 times minus 286. So the answer is X equals... So to get from here to here, which is X, that's the same as going from here, down here, and round here, which is with this arrow. So that's 4 times minus 394 plus 3 times minus 286. And then I would say I'm going against this arrow. So I'm going to go against this arrow, I'd write a big minus. I'm going minus 2,546. If I plug that into my calculator, which I'm not going to do because it's going to be a bit of a faff on this calculator. Well, what's the answer going to be? Let's have a little look. 20 plus 112. All right. So it's that. But there's the working for you. I'm nearly there. Excellent. Video's 24 minutes. And there's 23 questions here. So I'm roughly a mark a minute. And this is with all the explanations as well. All right. A gas cylinder contains 5 grams of propane, 5 kilograms of propane. How many propane molecules are in the cylinder? All right, so we've got 5,000 grams of propane. If they're asking me how many molecules there are in the cylinder, what you do is you work out how many moles there are first, and then you know that 1 mole contains this many molecules, because that's the number of molecules per mole. Look at the units per mole. So we've got to turn 5,000 into moles first, and to do that we need to divide it by the MR. The MR of propane is C3H8. 12, 24, 36 plus 8 is 44. So my first step is to work out the number of moles, which is 5,000 divided by 44. Calculator out. 5,000 divided by 44. Come on, phone. Somebody's trying to ring my daughter there. 5,000 divided by 44, 113.63 moles. 113.63 recurring moles. I've got this many moles, and there are 6 times 10 to the 23 moles, particles in a mole, and I've got 113 moles. So I'm just going to times it by 6.022 times 10 to the 23. I don't know how to do that on this calculator. I'm going to go onto my computer calculator, which you can't see, unfortunately, because that's got a scientific function. 113.63 times 6 and 10 and 3. It looks like I've got a huge number, 68178000000. It doesn't do it to but it's the 68 I'm interested in there. 21. C. Cool. Yeah. All right, that one. What sample of liquid has the greatest volume? All right. Well, density questions. Let's go through this again, because I mentioned this on. If you've not been watching my previous videos, you really should, because you're missing some good teaching. All right, that's modest of me, isn't it? But you are. 500 milligrams is 0.5 grams of pentane. So we're looking which has got the biggest volume. Grams per centimeter cubed. So what this means is, let me just talk about volume again. Each of these densities are measured in grams per centimeter cubed. So the density of pentane, they tell me that a 1 centimeter cube, a cubic centimeter of pentane weighs 0.63 grams. All right. So in this case, we've got 0.5 grams of something that weighs 0.63 grams per cubic centimeter. We've got less than a cubic centimeter. But the way that we do this, density equals mass divided by the volume. If you look there, mass divided by the volume, grams per centimeter cubed. So we've got a grams and we've got a density. So we've got a mass and a density. So if D equals M over V, I'm going to take the V up. V times D equals M. Mass divided by, V times D equals M. And therefore volume equals mass divided by density. So in each case, if I take the mass and I divide it by the density, I'll work out the volume. I'm going to tap away. Actually, I'll do it on the... I think it's useful for you to see me doing it on the phone here. Right, the first question then. I've got 0.5 divided by 0.63. So the volume here is 0.79. See, in the exam, you wouldn't have to go through this. So this would be really quick. You just take the mass and you divide it by the density. But the mass has got to be in grams, because the density is in grams. So this is not 650, this is 0.65. So the second one is 0.65 divided by 0.8. 0.81. This one is winning so far. 1.2 divided by 1.33. 1.2 divided by 1.33. This is winning so far, 0.9. And the final one, 1.3 divided by 1.48. 1.3 divided by 1.48, 0.87. This one, 22C. Not hard. Just grams per cubic centimetre. And this is the other one, density equals mass over volume. Just remember that. Quite often in chemistry, you're given density and a volume to work out the mass, then you can work out moles. But in this case, you were given mass and density to work out volume. So you need to be able to manipulate density values at A-level chemistry quite clearly. Which equation represents an initiation step? So initiation is where you have a molecule and radicals are formed from that molecule. All right, so this is a propagation step. This is a radical meets something to form something on a radical. So it's not you. This is a propagation step. Radical meets a molecule to make a molecule and a radical. Radical meets a molecule to make another radical. No, it's this one. It is D. You've got a molecule that looks like this, CH3, CF, Cl2. And what's happening here is one of these chlorines is breaking off, which is what happens, you see, because a carbon-chlorine bond is relatively weak. So when it's hit by UV light, you get these things forming. You get a chlorine radical, and you get this radical here. It's initiation step. Hope you enjoyed 30 minutes. I think in an exam, you could easily be hitting 1 mark a minute there. There weren't that many difficult ones in there, I don't think. But then again, I've been doing chemistry a while, so let me know what you think. Email me. Tell your friends to watch these videos, please. There are a few of you who watch these videos all the time, and there's loads of people who clearly aren't. You know, I know I'm never going to get massive view numbers because they're not great videos. But for you lot, they should be invaluable. And please tell your mates to watch them. Just tell them that they're good or that they're useful. All right. I hope you don't I hope you're not actually thinking that they're not useful. They're rubbish. But just if you're finding them useful, tell your mates. Because I want to help you. I'm getting frustrated as a teacher that I can't see you and I can't help you. I really like teaching chemistry. And I want these videos to get to as many of my students and students across the sixth form as possible. So, yeah. Share them with one another, please. All right? What to do, wave that way. Bye.